You know, every single app on your phone, whether it's for social media or your bank, is constantly juggling just a massive amount of data. And how they keep it all straight, secure, and super speedy, well, it's this fascinating balancing act. So today, we're going to pull back the curtain on the two big competing ideas that make it all possible.
I mean, really think about it for a second. Your home feed on, say, a streaming service, it feels instantaneous, right? It just loads hundreds of titles in the blink of an eye. But then, when you go and change your profile name, that change just magically appears everywhere, on every device, in every menu, perfectly. These two things feel so different, and believe me, they're happening that way for a very good reason.
The whole secret is in how the data is organized, its architecture. And to make this crystal clear, we're actually going to build our own little fictional streaming service from the ground up. Let's call it BingeBox. By designing its database, we're going to see firsthand the exact challenges and the really clever solutions that engineers wrestle with every single day.
Okay, so we're building BingeBox. Where do we even start? Well, the most intuitive first step, the thing that probably makes the most sense, is to just create one giant list. Kind of like a big, messy spreadsheet to track everything that happens.
So our first attempt might look something like this. A single table called Watch History. Every time someone watches a movie, we just pop a new row in there with all the info. The user's ID, their name, the movie's ID, the title, you get the picture. It's simple, right? One row, one watch event. What could possibly go wrong?
Well, as it turns out, a lot can go wrong. This super simple approach is actually a minefield of problems that developers call anomalies. And the biggest issue right off the bat is data redundancy. See how the user A. Smith's name is repeated over and over and over for every movie they watch? Same for a movie's title. This repetition, it's a ticking time bomb.
And here's the first explosion. Let's say a user updates their email. With our setup, we can't just change it in one spot. Oh no. We have to hunt down every single row in this giant table where that user appears and update each and every one. And if we miss just one, our database now has conflicting information. That, my friends, is an update anomaly.
Or what about this? We want to add a hot new movie to our BingeBox catalog, but nobody's watched it yet, so where do we store its title and genre? Our table is a watch history table. If there's no watch event, there's no row. The movie has nowhere to live. This is what we call an insert anomaly.
And finally, maybe the scariest one. Imagine a user watched some rare indie film, and they're the only person who ever has. If we delete their watch history record for some reason, we might also delete the only copy of that movie's title and genre from our entire database. Poof, the movie effectively vanishes. Yeah, our simple spreadsheet is a complete mess.
Okay, so how do we fix this chaos? We need a system, a way to organize our data intelligently. And this is where this beautiful concept called normalization comes into play. You can think of it as the art of tidying up your data.
So what is normalization? It's basically a formal process for cleaning house. The whole goal is to break down these big, messy tables into smaller, much more logical ones. And by doing that, we get rid of all that dangerous repetition and we seriously improve the integrity of our data.
The guiding principle behind it all is so simple, and it's really the core mantra of normalization. One fact, one place. It just means that each individual piece of information, like a user's name or a movie's title, should exist in exactly one spot, period.
Let's see it in action with our BingeBox app. Instead of one giant table, we create three smaller specialized ones. First, a users table that holds user info, just once per user. Second, a movies table for all the movie details, just once per movie. And now, our watch history table becomes incredibly simple. It just holds the IDs that link a user to a movie. That's it.
And just like that, look at the benefits. Data redundancy is gone. Those nasty update, insert, and delete anomalies, solved. Our data is way more trustworthy, the whole system is easier for new developers to understand, and changing things down the line becomes much, much easier. It's clean, it's efficient, it's safe. So, we're done, right? Problem solved?
Well, not quite. See, in fixing our data integrity problem, we've kind of accidentally created a brand new one, a potential performance issue. Our perfectly organized system might now be kind of slow.
So here is the crucial trade-off. To show you a list of movies you've watched, the app can't just look at one table anymore. Our watch history table only has those IDs. So the database now has to do this operation called a join.
It has to go look up the user ID in the users table, then look up the movie ID in the movies table, and then stitch all that information together for every single row. With millions of users, these joins can really start to slow things down.
And this is the point where engineers have to get really pragmatic. When speed is absolutely critical for the user experience, sometimes you have to intentionally break the very rules of perfect organization you just set up.
And that brings us to our second key concept, denormalization. Now, this isn't about just being messy again. It is a deliberate, strategic decision to add some of that redundancy back into the system, but only to optimize for speed on very specific, high-traffic parts of the app.
Let's go back to our BingeBox watch history table. To speed up that what you've watched feed, we might do this. We add back a copy of the username and the movie title right into the table. We call them cached, just to show that they're copies. Now, to build that feed, the app only needs to read this one table. No joins needed. It is way, way faster.
But here comes that trade-off again. We've gained all this speed, but we've brought back a risk. If that user changes their name, our app now has to be smart enough to update it in two places: the main users table and every single cache copy in the watch history table. It's more work when writing data, but it makes reading that data fly.
So what have we learned here? Well, it's not a battle of good versus evil. It's not normalization versus denormalization. It's really about finding the absolute perfect balance for each specific job the app needs to do.
And that's really the ultimate secret here. Modern, sophisticated applications, the ones you use every day, they don't pick a side. They strategically use both of these approaches, playing to the strengths of each one.
The professional strategy looks like this. You normalize your core, critical data, what we call the source of truth. Think about user accounts, payment information, subscriptions. This is data that must be consistent. Then you strategically denormalize for features that are read all the time, like home feeds, analytics dashboards, and search results. Places where speed is the absolute top priority.
This table sums it all up beautifully. Normalization's goal, data integrity. Denormalization's goal, raw speed. Normalization has very low redundancy and simple writes, but the reads can be slower. Denormalization has higher redundancy and more complex writes, but you get lightning-fast reads. One is for your core data, the other is for reports and those read-heavy features.
So next time you're using your favorite app, just think about this for a second. Which parts feel like they are built on a rock-solid, perfectly organized foundation, like your account settings? And which parts feel like they've been deliberately duplicated and optimized just to give you that instant, blazing fast experience, like a trending feed? I guarantee you the answer is almost always both.